All right, so I end up getting x. So instead of v naught x, I'm going to write this as v naught cosine theta times t. And 0 equals, instead of writing v naught y, I'll write v naught sine theta times t minus 1/2 g t squared. Oh, forgot. Oh, sorry. Oops. Cross that out. 0 equals v naught sine theta instead of v naught y minus 1/2 g times t. Okay. Now, if we look at these two equations, this one and this one, now we have a situation where we have two equations and two unknowns. The only two unknowns are theta and t. Okay, so we should be able to solve one of these equations for one of the unknowns, substitute that into the other equation, and solve for the other unknown. And so it's only a question of now how do we want to proceed. And I think the way that I want to proceed is, let me give this a little thought, is I'm going to take this equation and solve it for t. So if I take that equation and solve for t, I end up getting t equals, let's see, I'll subtract the v naught sine theta from both sides, then multiply by 2 and divide by g. I end up getting t equals 2 v naught sine theta divided by g. Okay. Now I'll take this and plug it in to that equation, which ends up yielding us x equals v naught cosine theta 2 v naught sine theta divided by g, which equals, all right, almost there, I think. All right, stay with me. If I collect the v naughts and make it v naught squared, I end up with something that looks like this: v naught squared times 2 cosine theta sine theta divided by g. And so now we need to be clever. Remember, we're trying to solve, if you look at this equation now, we know x, we know v naught, we know g. The only thing we don't know is theta. We have to be a little bit clever here in order to go any further, though. So we should be able to solve this equation for theta. And the problem is, though, that theta is actually in two terms. It would be nice if we could replace those two terms with one term. Well, it turns out there's a trig identity that says 2 cosine theta sine theta is equal to sine 2 theta. All right, so we can rewrite this as v naught squared sine 2 theta divided by g. All right, and so now all we got to do is solve for theta, and let's get the g and the v naught out of the way, and we end up with x times g divided by v naught squared equals sine 2 theta. All right, now if we take the inverse sign of both sides, we end up getting 2 theta equals sine, the arc sine, inverse sine of x times g divided by v naught squared. Okay, and so that means theta equals 1/2 arc sine, inverse sine, x times g divided by v naught squared. All right, so now we can plug in what we know. X is 28 meters, g is 9.8 meters per second squared, and v naught is, I never wrote it down, 19 meters per second. Plug that all into here, and you end up getting 49.47 degrees. Problem solved. Okay. Well, that's it. We're finished. Now, there is one thing to point out, and as you probably are aware, common sense, everyday experience, when you are, we call this situation, this particular projectile motion is an example of a situation that we call level horizontal flight. And the reason is because the vertical position where the projectile takes off is the same as the vertical position where the projectile lands. And you're probably aware from your experience that when you're firing a projectile, you can make it go the furthest if the launch angle is 45 degrees. Okay? And for any intermediate range, it turns out that, okay, so we just solved this problem and discovered that if we launch the balloon at 49.47 degrees, it will travel to 28 meters across the quad, landing in your friend's dorm room, making all of his physics homework soaking wet. But it turns out that there's actually another solution to this problem. This equation right here, the reason is because the inverse sine function is a little funky. And this equation right here, or I should say, there's two thetas. There's two thetas that make this expression true for a given x. That's not the maximum range. We found one of them, and the other one, let me just go to the next slide to sum this all up. Okay, so this is the equation that we just derived relating x, the horizontal range, with the launch angle if we know the initial velocity of a projectile for level horizontal range, when the landing position, the vertical position of the landing is the same as the vertical position where the projectile took off. So unless the launch angle is 45 degrees, there's two thetas for a given x that make this expression true. All right, one of them we can solve for using the inverse sine function like we did in the previous slide. The other one we can get to, so that would be at theta 1 from the inverse sine. The other one we can get by just taking that angle and subtracting that angle from 90 degrees. So in this problem, theta 1 was 49.47 degrees, which would mean that theta 2 is 40.53 degrees. Okay, so you can imagine, here's your dorm room, here's your friend's dorm room, and you can launch a balloon at 49 degrees, or you can use a more shallow trajectory and have the same range. Okay, there's two trajectories that are going to give you the same range, unless the launch angle is 45 degrees. And then that corresponds to the maximum range. But for a distance less than the maximum, there's two trajectories, two different launch angles that will give us the same range. Okay, well, I will end this discussion there, and I hope that this was helpful. And we've derived another equation that I'll put on your equation sheet for the exam, so we don't have to go through all that again. But remember that this equation is only valid for level horizontal range, where the vertical takeoff position is the same as the vertical landing position.